Everyone. So it's a great pleasure to have Miriam Benini from Parma, who's going to talk today on non-autonomous dynamics on the boundary of the disk and application to wandering domains.
So it's a pleasure to be here. Thank you so much for this invitation. I will talk about problems of non-autonomous dynamics on the disk, and in fact, on more general simply connected sets. And this will have application to some important problem in transcendental dynamics, which is the study of some sets which are called wandering domains. And as you can see, this is a joint work with a big group of people. It's myself from the University of Parma, Nuria Fageia from Barcelona, and Vasu Evdoridou, Phil Rippon, and Gwyneth Stollard from the Open University in the UK. So what is the problem? The problem is that, what is the problem that we are considering? We are simply considering, for the moment, a holomorphic function f, which goes from the disk into itself, and we consider its iterates, which means we compose f with itself n times, and the kind of idea is that you want to see what happens to points in the disk when under this iteration of f. So the idea is you take a point and you see what happens to this point after you apply f many times. We are especially interested in the asymptotic behaviors. And what happens to points in the disk is one question. Another question is, if you assume that you have some decent extension of your function f to the boundary of the disk, and many of you may know Fatou's theorem about the extension of bounded functions from the disk to the complex plane, they extend to almost every point in the boundary with respect to the Lebesgue measure. So under the assumption that our function f extends in some reasonable way to almost every point to the disk, we can ask what happens to points in the boundary under our iteration of f. And of course, the question of what happens to points inside the disk under iteration is much simpler, and we'll have a much simpler answer since our map is holomorphic from a bounded set into itself, while what happens to points in the boundary is more delicate, because your function, even when we extend it, is not continuous as a map from the boundary to the disk to itself. Let me be more specific, and then what we are interested in eventually. So this is a classical problem. If you just take a function from the disk to itself and you iterate it, we will see that there is a fairly complete answer to both cases, to the case in which you consider points inside the disk and the case in which you consider points in the boundary of the disk. So really the generalization today will be about what happens when we study sequences of maps from the disk to the disk. So instead of taking the same function f and keeping iterating this function over and over again, you can study sequences of maps, f1 from the disk to itself, f2 from the disk to itself, f3 from the disk to itself, and you consider kind of the orbits of points when you first apply f1, then apply f2, and then apply f3, and so on. And more generally, we will see what happens when it's no longer the disk, but it becomes a simply connected domain. So here really we have two pieces of generalization. One piece of generalization is to go from iterating one single function to iterating sequences of function, and another piece of generalization is what happens when you change the geometry of the domains. So instead of considering maps from the disk to itself, you consider maps between simply connected domains. These are the two setups. The basic setup in which you have one single function which is iterated on the disk, and the most general setting that we are considering today, in which you iterate a sequence of function gi in this case, and then you consider the composition fn, which is you apply g1 first, then you apply g2, then you apply g3, etc. Okay, and there is this intermediate setup in between in which we will consider a sequence of holomorphic function g1, g2, gn from the disk to itself, in which we, instead of considering one single function, which we consider iterates, but we remain on the disk. So in the case that we just have a function f from the disk into itself, which is holomorphic, what happens to points inside the disk is a very classical theorem, and it's called the Denjoy-Wolff theorem. And it tells you that unless you are a rotation, which means a generalized rotation, which means you are conformally conjugate to a true rigid rotation, z goes to e to the I theta z. So unless you're in this specific case, in which is a conformal map and which does not change the distances between points, unless you're such a generalized rotation, there is a unique point, which is called the Denjoy-Wolff point, which is in the closure of the disk. And all the iterates of all your points in the inside of the disk converge to this point uniformly on compact subsets of the disk. Now, there are two cases. Either this fixed point tau is inside the disk, and then you can check that it's actually a fixed point for f, so f of tau is equal to tau. And of course, there can be no other since everyone else is converging to tau under iteration. Or when it's in the boundary, you cannot extend, in principle, you cannot extend your function to the boundary, so you cannot say that it is a fixed point, but there are many more things that you can study, like the rate of convergence and many other more subtle aspects. But for us, the only crucial thing for today is to know that there is a dichotomy. When you have one single function, you either converge to a single point in the boundary, or you converge to a single point inside the disk. So the dynamics inside the disk is very clear in this non-autonomous setup. And what is less clear and needs some definitions is what happens to the dynamics of points in the boundary. Remember, we're interested in two types of problems in different setups, but the two problems were what happens to points in the inside of the disk, and assuming you have a decent extension, what happens to points in the boundary of the disk. So there is this very standard way, probably many of you are more experts than me in this type of problems. There is this very standard theorem which tells you that if you have a bounded function from the disk to C, which is holomorphic or harmonic, in fact, we will not need harmonic for today, then for almost every point in the boundary of the disk, you can define a map which is defined by taking the limits of your function along radii. So you have your disk, you choose a point in the boundary, you take the radius which goes from the center to the disk to the point of the boundary, and you look at the limit of the function when you move along this radius towards your boundary point. And Fatou's theorem tells you that this limit exists for almost every point in the boundary of the disk. Of course, the assumption that f is bounded is an overkill. What you really, well, the counterexample to Fatou's theorems are sets which omit only 3 points. And in fact, it's easy to see that just by a change of coordinates, it's not necessary for your function to be bounded. It's enough that it omits an open set, okay? So a direct consequence is that from this theorem, just up to making a Möbius change of coordinates, moving the point at infinity in a bounded point, you can see that an immediate consequence is that this theorem holds also when your image, when your f goes from D to some set which omits an open disk. But in fact, it's also even more generally, and if your map is conformal instead of being just holomorphic, it always extends for almost every point using these radial limits. So this will be the extension that we use, and as you see, it exists in many cases. Now, for the purpose of this talk, you can do things more generally, but for the purpose of this talk, we will ask that this boundary map that we define to radial limits really maps the boundary to the boundary. This is one of the possible definitions of inner function. So a function for a holomorphic function from this to itself is called an inner function if the modulus of this radial extension at star of zeta is equal to 1 for almost every zeta in the boundary for which it is defined. So all it says, an inner function is just a map from the disk to the disk. By Fatou's theorem, it extends almost everywhere as a map from the boundary of the disk to a priori the closed disk. But we require, for simplicity and for the purpose of this talk, it's not necessary, but for the purpose of this talk, we require that the boundary maps to the boundary. So that really, points in the boundary may or may not have an F star defined on them. They may be in a bad set. But if you look at the full measure set on which your boundary map F star is defined, almost all of these points will map to the boundary of the disk. And you have to be very careful. And of course, this is just one iterate, okay? We will want to iterate our map F star. So in principle, what we will really consider is the dynamics on the boundary not defined on every point of the boundary, because F star is not defined on every point of the boundary, but on the sets of points in the boundary on which all the iterates of F star are well defined. Since each iterate is defined up to a set of measure 0, basically we look at the intersection of sets of full measures. So there is a set of full measure on which all the iterates of our F star are defined. And all the types of results that you get for maps from the boundary of the disk to the boundary of the disk, since these maps are, even by definition, just defined on sets of full measure, will be in terms of measure. So there will be no result which say for every point, like for the points in the interior, the results will be for almost every point in the boundary. And there are really, so when we look at the dynamics on the boundary, there is really a dichotomy on what can happen. And this is the idea of the dichotomy. Before I give you the theorem, I need to give you the definition of the types of dichotomical behavior that you can have. So a map from a space into itself, everything is measurable in this setup, is called recurrent if for every measurable set which is backward invariant, you have that the measure of the pre-image of this set intersected with the set is, you have that the pre-image of this set is full measure inside your set. Now, this, if you're not familiar with this type of concepts, is a bit mysterious, but what it implies, so what is interesting for us, is that it implies that every point, almost every point in your measure space comes back to itself infinitely many times, close to itself infinitely many times, okay? So it really means if a map is if a map is recurrent, it really implies this definition of recurrence, which is the definition from Dering and Magnier in the paper from 1991. There are many different definitions of recurrent maps, but this definition is, it implies that orbits of points keep coming back to themselves. A completely opposite behavior is the case in which even on the boundary, iterates of points converge to a point, okay? And again, the convergence needs to be defined almost everywhere because not even your map is defined on the entire boundary. So really, if you, in our case, we will need to consider convergence of points on sets which have full measure. So we will say that the function f converges to a point tau almost everywhere if it converges, the iterates of your function converge to the point tau for x in a set of full measure. And our setup will be exactly the case in which the space is the boundary of the disk, the measure is the Lebesgue measure, and in fact, we will need to use the harmonic measure as well, but for the disk, this is absolutely continuous with respect to the Lebesgue measure, and our map F will be the boundary map of some inner function. So this is the theorem of what happens in the boundary, and it's a result by Dering and Magnier from 1991, though there is also some previous work by Aronson in 1978. So we have our inner function from the disk to itself. If the Denjoy-Wolff fixed point, okay, so we have a Denjoy-Wolff fixed point to which all the inside orbits converge to, okay? If this Denjoy-Wolff point is inside the disk, then the map on the boundary is recurrent. So basically every point, the orbit of every point comes close to itself infinitely many times. On the other hand, if the Denjoy-Wolff fixed point is on the boundary of the disk, there is really a dichotomy. There are two possibilities. If your orbits from the inside converge to the boundary slowly, then again, you can show that your map is recurrent, and slowly has a precise characterization. Okay, we will get back to this later. On the other hand, if your orbits converge to the boundary quickly, and again, this has a precise characterization, you will see that this is where geometry of the domain comes into place. Then the iterates of your function converges to the Denjoy-Wolff fixed points almost everywhere on the boundary. Now, this is kind of a, let's call it poetic interpretation. So if the Denjoy-Wolff fixed point is inside, your points on the boundary don't know what to do, so they keep wandering around. If your Denjoy-Wolff fixed point is in the boundary and everybody converges to it very quickly, then they carry the boundary along, and they bring and also points in the boundary converge to this Denjoy-Wolff fixed point in the boundary. If the convergence to the Denjoy-Wolff fixed point is on the if the Denjoy-Wolff fixed point is on the boundary, but points in the inside converge slowly, still the boundary points have freedom to move around and are not carried away by the flow of the points in the inside of the disk. So I would like to tell you a bit more about what happens in this case in which the convergence to the boundary is quick, because this is kind of where this mysterious geometric condition, there is this, so quickly means that the distance between the orbits of your point and the boundary decreases very quickly, and hence the sum of the distances of your orbit from the boundary is less than infinity. And I would like to show you why this condition is the correct one, where the geometry of the disk comes in when we look at this condition. But I need to define the harmonic measure on simply connected sets. So again, many of you know this better than me, and the standard definition of the harmonic measure is in terms of the Poisson kernel. However, for us, for today, there is an equivalent definition which is in terms of Riemann maps and in terms of pullbacks of the Lebesgue measure. So we take a simply connected open set. For now, let us just look at the left part of this picture, okay? The one we have the disk and the simply connected open set U. So we have a simply connected open set U. By the Riemann uniformization theorem, there is a conformal map phi, which goes from the disk to our U, and we can choose that Z is a bit central, but it should be near the black dots. So this Z should be here, okay? And how Riemann maps 0 to some marked point Z, which is a bit away from its mark. And we define, so clearly the Riemann map depends on how you choose this base point in U. There are infinitely many Riemann maps, and you can choose. You have a lot of freedom in choosing both your base point in U, so the point that you want to be the image of 0, and the derivative, but we are not interested in the derivative today. It's only the base point which matters for us. So we choose a Riemann map phi, which maps 0 to a certain point Z in U, and we want to define the harmonic measure of some subset A of the boundary, which for today, for the purpose of this talk, is an arc, but in general, it will be a measurable set. Okay, what do? We can look. So our Riemann map goes from the disk to U, and it extends almost everywhere. For almost every point to the disk, it extends to a map from the boundary of the disk to the boundary of U. So many points in the boundary of U, not all points in the boundary of U, but many points in the boundary of U, the so-called accessible points, will be images under the extension of this Riemann map. So let us call the pre-image of this set considered in this sense. So the points in the boundary of the disk on which the radial extension exists and which map to the boundary, and in fact this boundary is smooth. So in this specific picture, everything extends. Anyway, so let us consider the pre-image of this set A on the boundary of the disk. This has a certain Lebesgue measure. This will be the measure that we will say is the harmonic measure of the set A with respect to the point Z in the domain U. Okay, so for the purpose of this talk, the harmonic measure is just the push forward, of the Lebesgue measure on the boundary of the disk. Now notice that it is true that on the disk we have the standard Lebesgue measure, but if we consider conformal maps from the disk to itself, so if we choose a marked point Z on the disk, we can as well consider the Riemann map, which maps the disk to itself and which brings 0 to this marked point Z. And if we look at it in this way, we can define the harmonic measure in the disk with respect to this marked point Z as the push forward, or if you want, as the Lebesgue measure of the pre-image of our set under this Riemann map, okay? So And we will see that there is something very nice. So if this point Z slowly approaches, so there is a nice geometrical interpretation of the Lebesgue, of the harmonic measure in terms of random walk. I'm going to tell it because this will make something clearer later. You can imagine the harmonic measure. Now forget about the Riemann map, okay? Now you are in your set U or in your disk D and you fix a market point. Let us work it in the disk. You can say that the harmonic measure of a set A is the probability of starting a random walk at Z and finishing it when you hit the boundary exactly in the set A. So as you can imagine, the closer your starting point is to your set A, the higher the probability that you are going to end up in A. So as you move your base point towards the set A, the harmonic measure of the complement of an arc will become negligible. Let us see why we care about it. So let me see if I manage to write. So let me try to show you that quick convergence of points to the boundary implies that, sorry, let me show that if there exists a point, so the part of the theorem by Döring and Magnier that if the convergence towards the boundary is quick, then everybody in the boundary must follow the internal dynamics. So the claim is that if there exists a point Z in the interior of the disk, and f to the n of Z converges to the Denjoy-Wolff fixed point, which is in the boundary, quickly enough so that the sum of the distance between Fn of Z and tau is sum over n is less than infinity, then almost every point in the boundary of the disk also has iterates which converge to tau. So, and the reason why I want to do it is because I want to highlight, as I said before, that this condition of the sum being convergent really depends on the fact that the boundary of the disk is smooth. So for simplicity, let us assume that tau is equal to 1. And so, how does the proof go? So, wait. Okay, it's working. So how does it work? The idea is to consider a sequence of nested arcs near your one. And for each one, and you will choose sequences of arcs which are smaller and smaller. And for any such arc, we consider the set of points. So here we have our action of F, which morally goes from the closed disk to itself, though this must be intended up to measure 0 sets on the boundary. And for any arc in this collection of nested arc, consider the points, which I'm going to say it and then I'm going to write it down, which are in the boundary, will move around, but at some point they will fall in your marked arc S and will stay in there forever. And believe it or not, so let's consider points which eventually, whose orbits eventually stay in S. And you can write this as, well, you want your points to eventually stay in this arc S. So you want that from a certain point on, all of their iterates stay in your arc S, which is the same as saying, so points in the pre-image of S will map to S after one iterate. Points in the pre-image of S will map to S after 2 iterates, and so on. And you want points which eventually stay in S forever. So you want points which are in the intersection of the pre-images of this arc taken over some n, which is sufficiently large. But then, of course, it doesn't matter at which big n you start. So your say attracting basin of this arc S in a very improper way is just the union of the over any n bigger or equal than 0 of the intersection of all these pre-images of the arc S. I don't know if this is clear or if it was too quick. Let me repeat it very quickly, just because I think I was a bit quick. So you fix an arc and you want to see the set of points which eventually land in S, and once they get in S, they stay there forever. And you can write this as the union over big N bigger or equal than 0 of the intersection of all the sufficiently high pre-images of S, because this will just tell you that your orbits Fn of Z, so Z is a bad name, Fn of X belongs to S for all n bigger or equal than n, and of course it doesn't matter where you start, so you can take the union over n bigger or equal than 0. And we want to say that this set has full measure. Lebesgue measure, okay? On the disk we have this mass of Lebesgue and harmonic measure. So we want to say that this set has full measure, so this is the same as saying that the complement has 0 measure. And what is the complement? The complement, if you remember this gymnastics with countable sums and countable unions and intersection, the complement is just the intersection over big N bigger or equal than 0, union over n bigger or equal than big N of Fn minus 1 of the complement. Okay, so instead of looking at the points which come into S and stay there forever, we consider the complement consisting of points which, no matter how far or how long you iterate, they will always exit their orbits exits infinitely many times. And let me point out that if we show that for each arc this set AS has full measure or the complement has 0 measure, then we win, right? Because who are the points whose orbit converge to 1? They are the points whose orbits enter smaller and smaller arcs centered at 1 and then never leave again. So really the points whose orbits converge to 1 are really the ones who are in the uncountable intersection of, well, in the countable intersection of all these nested arcs, if we take them to be a countable sequence. And so if we can say that this set of points which come into each arc and stay there forever have full measure for every such arc, then when we take the countable intersection of full measure sets, it's still full measure, and hence we get that the set of points whose orbit converges to 1 has full measure. So now this is where the harmonic measure comes in. Because there is something called, so the idea is to use the harmonic measure, okay? Before I tell you exactly how I use the harmonic measure, let me tell you something about which is called Ransford inequality, and which tells you how the harmonic measure of points of sets in the boundary gets transformed when you apply functions. So this is something called Ransford inequality. It may have other names in other setups, but it tells you this: that if you have a function, if you have a set A in the boundary of the disk, a function f, well, we need to discuss this, huh? This f from the boundary into itself. Give me a second. I'm going to write the claim, and then I tell you what the assumption needs to be. So if you take a set A in the boundary of the disk and you look at its harmonic measure with respect to some base points, which need to be the iterates of points, then this is bigger or equal than the harmonic measure of the pre-image of this set, still in the disk, with respect to a certain base point. Let me tell you two things about this. So what does this mean? It means if you have a set on the boundary of the disk, and I want to estimate the measure. This is so. In my view, this is telling you that the boundary maps is kind of expanding for the harmonic measure. Okay, and in geometric in pictorial view, this is telling you that if you have your function, that in our case will be Fn, which goes from the disk into itself, and you look at the image of a pre-image. This is considered in terms of sets. So the set of points which map to A under F to the N. If you look at this pre-image on the disk, the harmonic measure of this set is less or equal, with respect to a certain base point Z, is less or equal than the harmonic measure of the nth image of this set with respect to the nth image of our base point. So there is a bit of a catch here, because the classical Ransford inequality only works on sets on which your function extends continuously. So you can prove some generalized version of this. It's not completely clear yet if it works for measurable sets, but it works for open sets, and so it's enough for the proof. So you will wonder, did we gain anything? It doesn't quite look like we gained anything for now. Okay, but yes. Why? Because you recall we had this Z such that the sum of 1 minus modulus of Fn of Z was less than infinity. Okay, and this will be the base point that we will consider here. And so what is, do you remember AS? We wanted to say that the measure of this set, A of S complement, was equal to 0, and this was defined as the intersection over big N, the union over small n of the pre-images of the complement of our arc. We wanted to estimate this, but now we use basic measure theory. And what is the measure of this set? Since I wrote it as countable intersection of a countable union, I know that the measure of this set is less or equal than the inf over big N, this is the intersection part, of the sum of all these measures of these sets. So of the sum of the mu is not mu, it's a harmonic measure. So the harmonic measure of my with respect to this point Z of my set A of S complement in D is less or equal than the inf over N, the sum of the harmonic measures of all these sets of which I'm taking the union. So the harmonic measure with respect to Z of these sets, which are Fn, F minus N of the complement of the arc in D. But now for this one, for this set, we know that we have this Ransford inequality, which tells us that this is less or equal than the harmonic measure with respect to, I have to change the base point, so I have to take as base point F to the N of Z of the arc itself, which is now fixed in D. And can we say something about this? Let us see. Let us draw a picture of this. So this set, so we have to look at the harmonic measure of this arc, the complement of an arc centered at 1, when I take for base point f to the n of z. So what is our picture? We have our disk, the complement of an arc centered at 1, and we have our base points, which are f to the n of z. And what are they doing? Well, by hypothesis, they are converging to 1 quickly. And here, there is a geometric estimate, which is due to Pomerenke, I think, but which you can reprove by hand using the definition of harmonic measure in terms of Poisson kernel, which tells you that the harmonic measure of such an arc goes to 0 as your base point goes to the opposite, diametrically opposite point. How? Linearly in the distance. This tells you that omega, as I take for base point of n of z, of this complementary arc in D, goes to 0, is less or equal than some constant, which will depend on the arc, but we don't care, times the modulus of fn of z minus 1, and this will be to the power 1. And this is really because the boundary is smooth. And then you win, because if you remember the equation we had, this will become the sum of the distances between your orbits and 1, which we assumed the full sum was less than infinity. So when I take the tail, this is the union from big N to infinity. When I take the tail, this goes to 0. Now, why did I go through all of these details? I never go into details during talks, but what I want to say here is, so what does this proof use? This proof uses 2 fundamental things. One thing is that this transport inequality, which tells you that the harmonic measure gets increased when you take images of sets on the boundary. It's not completely true if you say it like this. It's true when you write it in the reverse way like I wrote it. But morally speaking, if you want to know the measure of a set, you can look at the measure of its preimages, and the measure of your set is going to be bigger. Or if you want, the measure of your preimage is going to be smaller, up to changing the base point accordingly. And the other thing is that once you have this, you need to know how the harmonic measure behaves when your base points converge to the boundary. Now, let me go back to the presentation. And let me go back to the presentation. After all this math, I promise that was the only proof that you will ever see. And consider sequences of inner functions on the disk. Okay, so what did we do here? We looked in all this math. We looked at the fact that if you have just one map which iterates on the disk, you have your Denjoy-Wolff fixed point, which can be in the inside or on the boundary. And if your Denjoy-Wolff point is in the boundary, but the inner orbit converge very fast, where very fast really depends, the notion of very fast really depends on the geometry of your domain, on this estimate, on how the harmonic measure behaves when you go to the boundary, then you get that also almost every point in the boundary converges to the same Denjoy-Wolff point. Now, let us look for a minute at sequences of inner functions from the disk to itself. Okay, so we keep the geometry. The geometry is still maps from the disk to itself, but now we have a countable family of maps, and we consider instead of considering the edges of a single map, we consider the maps Fn. Now n is in the bottom instead of being in the top, and this is just first I apply G1, then I apply G2, then I apply Gn, and so on. So the first question is, what happens to the internal dynamics? Do you still have a Denjoy-Wolff point? And here one may pause and ask. And by the way, what is a Denjoy-Wolff point in this context? Okay, because let us think a second. If you take a point which is in the inside of the disk, and you consider all orbits which get asymptotically close to the orbit of your point Z0, well, they all get asymptotically close to each other. So in fact, any point in the set of orbits which converge together could act as a Denjoy-Wolff point, could be considered a Denjoy-Wolff point, or even more precisely, a Denjoy-Wolff orbit. What makes the Denjoy-Wolff special? So even if you look at it in the autonomous setting, so in the setting where you have only one map, how can you interpret this? You have a Denjoy-Wolff point means that the distance between any two orbits gets close, so any orbit gets close to the Denjoy-Wolff point, whose orbit is fixed because it's a fixed point, and hence any two orbits get close to each other. And in this case, what makes the Denjoy-Wolff point special is that it's fixed under F. So it's really F of tau equals tau. When you're in a non-autonomous setting, it doesn't really make sense to think about a fixed point. So in this case, probably the correct definition of the Denjoy-Wolff orbit would be to say that a point as a Denjoy-Wolff orbit is for every point in the disk. So this point can be in the interior or in the boundary, exactly like in the autonomous case. And we can say that this is an Denjoy-Wolff orbit if every point inside the disk has an orbit which converges to the orbit of our, say, Denjoy-Wolff orbit. Okay, so this is the most immediate definition of the Denjoy-Wolff orbit. And now, of course, the question should be, so do you have something like the Denjoy-Wolff theorem in this case? And the answer is, as you may expect, not in general. So in fact, you can construct sequences of inner functions, which are not Möbius, which was basically the special case in the Denjoy-Wolff theorem. And each orbit is contained in a compact set, so they don't converge to the boundary, okay? They stay inside the disk. But the distance between any two orbits is bounded away from zero. Okay, you cannot think it is bound to be uniform, obviously, because you have points arbitrarily close to each other. But you take any two orbits, and they're not going to converge together. They're going to stay away. And this is kind of a counterexample of the existence of a Denjoy-Wolff orbit in the case that the candidate Denjoy-Wolff orbit would be in the interior of the disk. You can also construct counterexamples of Denjoy-Wolff orbits in the boundary of the disk. Now, what you can prove is that that this kind of behaviors are uniformly in Z. So either, I didn't put this theorem, but what you can prove in this case is that either all orbits converge to each other, so the distance between any two orbits goes to zero, or the distance between any two orbits does not go to zero. This is what you can prove. And you can also kind of prove that if a point goes to the boundary in a certain sense, everybody does, and so on. So you can prove some uniform results on the behavior of points in the inside. But clearly, the Denjoy-Wolff dichotomy that we have in autonomous setting cannot work. So you may wonder, is there actually anything that you can prove in the non-autonomous setting? And the good news is that this theorem about convergence of the boundary to a convergence of inner points to the boundary being quick does work also in the non-autonomous setting. So what can you prove? You can prove that if you have a sequence of inner functions from the disk to itself, and there is a point whose orbit converges to the boundary, notice that I'm not saying it converges to a Denjoy-Wolff orbit, okay? This is a different setup problem. So, but let us assume just for now that it converges to the boundary. Then every orbit in the disk converges to the boundary, which is already something nice, okay? That you don't have some points whose orbits stay inside forever and some orbits whose orbit converge, some points whose orbit converges to the boundary. And moreover, if the convergence is quick, so the same condition that we had before, that the distance between your orbits and the boundary is less than infinity, the sum of the distances between your points in the orbit and the boundary is less than infinity, then also in the boundary, everybody converges to the same orbit. There is a typo here. So there is a point inside the disk, the orbit of this point converges to the boundary, then every point in the boundary also converges to the orbit of your point inside the disk. This is a point Z naught, sorry about this. So somehow, an orbit in the disk, if it converges to the boundary quick enough, obliges all the orbits in the boundary, which a priori have nothing to do, to converge with her to the boundary of the disk and basically follow the orbit of this inside orbit. Well, On the other hand, one can construct counterexamples. So you remember the results on the boundary were of two parts. One which was saying you that if you converge to the when the Denjoy-Wolff point is in the inside, you had that on the boundary the dynamics was recurrent. When the Denjoy-Wolff point was in the boundary, you had this dichotomy that either everybody was carried along towards the boundary orbit, or the dynamics was still recurrent. And in fact, to this case in which the convergence to the boundary slowly, you can show that there are that you can construct examples of sequences of maps which for which the boundary dynamics is not recurrent. But let's skip this for now. Now, what I would like you to notice is that this condition, now we replaced regular dynamics, so iterating one single function f, we replace it with sequences of functions, okay? And the geometric condition stayed exactly the same, because with a little bit of care, the proof that I gave to you really generalizes also to this non-autonomous setting. What makes things really different is when you replace this disk by simply connected domains UN. So in the moment that you have a sequence of functions, it's totally natural to consider more general simply connected sets. And simply holomorphic sequences of holomorphic maps from one set to the other, or if you want, from a set U0 to the set UN. And again, you have to, it's more delicate here to define boundary extensions. You need some condition on the sets. And you need to assume that kind of the boundary maps to the boundary. Well, this is not true. You can do stuff more in general, even for holomorphic self-maps of the disk. I don't want to get into this, but for this talk, the boundary maps to the boundary, up to sets of harmonic measure 0, because now the measure on the boundary is just a harmonic measure, okay? For the disk, we use the harmonic measure, but the reference measure is the Lebesgue measure. But once we have simply connected domains, what really matters is the harmonic measure on the boundary. Unfortunately, geometrically, do you remember we had this estimate? At some point, we needed to estimate the harmonic measure of sets which were far away from your base point, okay? For the disk, the measure of these sets was clearly going to 0, and it was going to 0 like the distance of your base point to the boundary. For general sets, the best that you can do is to use something called the Miu-Schmidt inequality, which tells you that the best estimate that you can get on how the harmonic measure of these sets far away go to 0 is in terms of the square root of the distance to the boundary. So in this case, really the best theorem that you can get is that if you have generic open simply connected sets for which the extension is decent, then what you need to assume is that the distance, the square roots of the distances of your orbits from the boundary are less than infinity in order to make the proof work. And of course, you have counterexample if you don't take this optimal condition. And there are many conditions, and then you can prove the same theorem, okay? You just need to modify the condition, because in that step of the proof, where you needed the geometric estimates on how the harmonic measure goes to 0, all of a sudden, you cannot use the modulus of the distance to the boundary, you have to use the square root of the modulus of distance to the boundary. And what I found interesting is that there are many conditions that can make this exponent alpha, instead of being 1/2, to be any number between 1/2 and 1. And it really depends on how much exterior space you have to your domain. So if you have a corner of angle alpha, you will get here an exponent which depends on alpha, and so on. All this, and it will last 1 minute, was to look at wandering domains. Now, wandering domains, if you're not familiar, you should just think about having an entire map. Okay, now we just have one map, but instead of going from the disk to C, or from the disk to the disk, or from the disk to another simply connected domain, is an entire transcendental map from the complex plane to the complex plane. And there are some strange domains, which are called wandering domains, which are just simply connected open sets, which have somehow a natural boundary. So they're kind of maximal in their own sense, which map one to the other. And though F is defined globally, when you look at your function restricted to these domains which move around, it's really like a non-autonomous system. And you can study it, and look at what happens to the dynamics on the boundary of these wandering domains, and generalize and use all these theorems that you prove to prove results about these dynamics. I think this is enough detail for today, and thank you so much for listening. Let me stay here.
Thank you very much. Very nice talk. So, if there are questions, comments?
Maybe I have a naive question. In your last results, what do you mean simply connected?
So you mean this theorem about wandering domains?
Right. Okay. Or even the one before, when you have a sequence of regions.
So the sequence of regions is a general theorem. And the setup is very general. You have simply connected sets which map one to the other under maps which are completely unrelated to each other. So this is a general theorem which generalizes non-autonomous systems on the disk, which generalizes iteration of inner function on the disk. This is a general theorem. Here, you don't need to know anything about transcendental dynamics on the complex plane. Now, all of a sudden, you go to the complex plane, and you have an entire transcendental function like e to the z. E to the z has no wandering domain. Well, a simple function, an entire transcendental function, but there are many transcendental entire functions which have this interesting dynamical feature that you can find open sets which map one to the other, and they're kind of maximal. They're really like components, domains, well, which form is, how do you call it? A subset of the dynamics. So your dynamics is on the entire complex plane. On the entire complex plane, you can extract the sequences of sets, and the specialty of this set is that the set U1 maps to the set U2, which maps to the set U3, and they never intersect each other. So you have that uj intersected uk is equal to the empty set for every j different from k. So really, you should imagine sequences of these joint sets in the plane, which map one to the other. So once you have this setup, it really goes back to the general setup that we have in this abstract theorem. And so what we proved in this abstract theorem, and in fact, several more results, can carry on to this setup, which is of interest of transcendental dynamicists. You take this sequence of wandering domains. I put bounded, but you don't need bounded. You need a much more general condition, but it's not worth stating it. Then, if you have one interior orbit which converges to the boundary, everyone in the interior does. And, well, there are more results that I'm not going to talk about, but the generalization of what we said in the general theorem is we have a point in the interior of one of these wandering domains, and you look at the distance of each iterates from the boundary of the nth wandering domain, and you assume it goes to zero quickly, so this convergent series condition, then almost every point in the boundary with respect to the harmonic measure also converges to this interior orbit. I don't know if this was the question and I answered completely. Was that the question?
Oh, you answered. Thank you.
Okay, perfect.
Yeah. Thank you.
Other questions? So I have two, Miriam. So the first one is about the type of convergence that you use. I mean, this quick convergence or not. Can you reformulate this type of convergence in something, let's say, more natural from an iteration point of view, like something like non-tangential convergence to the point, or tangential convergence, or something more intrinsic, or not?
I don't think so, because I think here it's really to use that estimate. I don't think so, but maybe. Okay, wait. Maybe if you have, maybe if you know that you have but no, I don't know. I don't think, but maybe you can make this exponent a little bit better if you assume that your convergence is non-tangential, but I'm not sure. I think we would need to go back to the disk and see. Maybe you can make, you are asking whether you can make this exponent a bit better. clearly not in the disk for non-autonomous because there is really a dichotomy in Dering and Magnier. Maybe for more general sets, you can do a bit better if you know that your convergence is non-tangential, but not with the methods we use.
Okay.
Because the methods we use are based on harmonic functions. So there is no tangential.
Yeah, but there are some relation between harmonic function and non-tangential or tangential convergence. That's why I asked. But
okay, then I don't know the answer. But if you know, I'd be happy to know.
Because morally, I mean, if you take the harmonic measure on one side of your Denjoy-Wolff point, then it converges tangentially close to that one if the measure along the orbit is essentially goes to 1 if you keep this smaller set, because it's the probability not to go there, start with the Brownian motion from the point.
Right.
So maybe that's why I came to this question. But then I have another question, which is kind of, okay, so morally you define a kind of Fatou set on the boundary, both for autonomous or non-autonomous.
Yes.
So I'm asking about the complementary, let's call the exceptional set, where still you might have existence of a radial limit for the function and the iterates, so it makes sense to talk about the behavior. You might have a boundary fixed point, which of course, they stay fixed, and so they do not belong to the set where you have convergence to the boundary. I mean, in case where you have the convergence. I mean, so the question is, do you know some other kind of point, something like maybe a point which is wandering, although for almost every other point they converge to the Denjoy-Wolff point, or maybe they are periodic, or?
I don't know, but to talk about periodic, you need to be in the autonomous setting, right?
Yeah, okay. My question was mainly for the autonomous setting, and of course,
I don't know. I think it's an interesting question, and in general, I think it's also a very interesting question to define a Julia set and the Fatou set in the boundary for the non-autonomous. So there is a lot. I think there is a lot to say here, and we have been working a bit on all of this, but I don't have a specific answer to your question. I'm sorry about this.
Oh, no problem. That's just a curiosity. Okay, other comments?
I have another question.
Yes, please.
Okay, about this theorem you're showing us now, you have the hypothesis that the domains are bounded. Is this a technical hypothesis, or do you have a counterexample?
No, we don't need it. We don't need them to be bounded.
Sorry?
We don't need them to be bounded. We just need Fatou's theorem to work.
So also the last point in which you have an estimate on the distance, on the sum of the distance being bounded, you get you get the same result.
Yes. So this is the worst estimate that you can have. If your boundaries of the wandering domains are C2, not that there are many wandering domains with C2 boundary around, but like Bach-Thaler has constructed some. So if your boundary of your domains are, for example, C1 plus epsilon, then you can reduce this to 1. This has nothing to do with being bounded or unbounded. This is the best geometric condition that you can put, which works for everybody. But if you have a bit of a better condition, then you can change this 1/2 to 1 or to some better power.
Okay.
And being bounded is really, you just want Fatou's theorem to work. So this is why it's in parentheses. You don't need bounded. This is irrelevant.
Okay. Okay, thank you.
Well, you need to do some work. You need to check that there are countably many accesses to infinity, so that infinity does not appear too often on your boundary, because it's an essential singular. I mean, you need to work a little bit to get rid of the bounded, but there is no bounded in the theorem.
Okay.
Thank you, Miriam. Other questions? Okay, so if not, we thank Miriam again. Thank you very much.